Now that we've spent some time converging on linear programs as a practical optimization problem that can be solved, we've spent time seeing why general optimization can be troublesome, and slowly reduced our set of possibilities until realizing that linear programs have these massive advantages, it's time to actually begin talking about solving linear programs. So before we can do that, it's convenient to put all of our linear programs in some common form. And we're going to end up calling that, standard form, maybe you guessed. We also ideally want a way of solving that last loose end from the previous lecture, which was that sort of earth-shattering claim that if we have a linear program with certain behavior, in particular that it has a polytope with vertices, that the minimum or maximum that we're looking for actually occurs at one of those vertices, and therefore that we can limit ourselves to looking at vertices if we're trying to solve it. The problem is, what about a case where the linear program, the polytope, doesn't actually have any vertices? Well, we actually can force that too. We can rewrite our linear program in a way that guarantees that there will be vertices of the polytope. And the standard form that we're going to develop will achieve that as well. The other reason we need standard form, of course, is that eventually we want to implement algorithms that solve linear programs, and that process benefits quite a bit from not having too many special cases. Obviously, a linear program in general is just the combination of any linear objective function, regardless of how you write it, and a set of linear constraint functions. And the constraints in general can be inequalities or equalities. They just have to be linear functions. So it is valid to have a constraint that looks like this. X plus 5y is greater than or equal to 7. It's also valid to have sort of strange-looking linear functions like 5 minus 2y equals negative x. I mean, it's weird that you'd write a linear constraint like that, but that is a linear constraint. And so is this. In general, whether I use a less than or greater than sign, whether I use an equal sign, whether I write my coefficients in a funny representation, it is still a linear function. It's still linear in terms of the variables. Obviously, we want to avoid cases like this. This one especially is sort of ridiculous. It's reasonable to expect that people providing us with linear programs actually bother to do their own arithmetic and, would call this 3 and not 5 minus 2. But we also want some way of uniformly handling greater than or equal to, or less than or equal to constraints without too much extra trouble. And the solution is going to be defining what's called a standard form that forces all of our constraints to be less than or equal to constraints. In this lecture, we're also going to talk about something called dictionary form, although really dictionary form is not another type of standard form. It's a way of representing a standard form LP that's going to be very useful in the next lecture. So it's just an example of shuffling material around so it fits neatly into each week. So our goal is to remove as much variability from the way a linear program looks as possible. So the first thing we're going to do is we're going to assume that we only ever have to solve maximization problems. And the claim here is if you give me a minimization problem, I can convert it to a maximization problem, solve it, and then hand it back to you. I don't actually need to do anything special to solve minimization problems. So here's a minimization problem. And I want to prove that I don't need special logic to solve this. If you give me a solver for maximization problems, I should be able to solve a minimization problem too. First observation, the constraints have no bearing on minimization versus maximization. We saw in the last lecture to some extent, the constraints define a set of points that are potential candidates to be the minimum or maximum. The set of points defined by the constraints doesn't change if I change my criteria from min to max, or in fact, if I modify the objective function at all. And we'll see later in the course that there are clever ways to modify objective functions that can really make our lives easier when we're solving certain types of LPs. So what I want to prove is that the fact that I'm doing minimization changes basically nothing. So the way I'm going to demonstrate that is by pointing out that if I have some function that I want to minimize, then what I could do is I could just negate it and then maximize that. The smallest value that f takes on will also be the largest value that negative f takes on, except with the sign flipped. If I negate the function f and then maximize it, I guess the value I get back will be negative, so I have to then negate it again on the way out. But I can phrase any minimization problem as a maximization problem and vice versa. The same transformation applies in reverse. And so for what it's worth, we could be doing the entire course in terms of only minimizing things. But for a lot of reasons, mainly for consistency with our books, we are instead going to do the entire course with maximization in mind. But we now know that we can convert minimization to maximization painlessly. All we have to do is flip a couple of signs on the way in and on the way out. Now, if you don't believe me, let's consider unconstrained minimization of this function here. I'll leave it to you to work out the gradient and set it to 0. But if I were to minimize this function f, I would get the minimum value 5. If I were to maximize the function negative f, keep in mind that the gradient of negative f would just be the negation of the gradient of f, unsurprisingly, then the maximum would be negative 5. But of course, if I want to compute the minimum of f, I would first compute the maximum of negative f, which is negative 5, and then I would negate that to get 5, which is the answer I expected to begin with. And one point that maybe we just have to save for later, because it's not as obvious why this is an issue now, but in general, if I'm looking to minimize or maximize a function, I may not just want to know the optimal value. I might want to know a vector x, so some argument that actually gives me that optimal solution. So it's important that I can establish not only that the solution is the same both ways, that the minimum and maximum can be interchanged, but also that the set of vectors that solve each problem is the same. So if I have a particular vector x star that gives me the minimum of f, it turns out that the same vector x star will give me the maximum of negative f, the negated maximum of negative f. That's a big deal because I need to know that the set of optimal solutions is the same in both cases. So therefore, what I could do is I could take, if you hand me a minimization problem, I could rewrite it as a maximization problem where I just take the objective function and I negate it, and I make a note to myself to negate the outcome when I'm done. So in this course, consistent with the book, I will use this notation negative max to indicate that I'm doing a maximization problem. I'm doing it all the way through, and when I'm completely done, I take the optimal solution and I negate it. So negative max means do maximization as normal, negate the final result when you're completely done. And I could say the same with like negative min or something, which I think we'll see later in the course, a couple of cases where we have to convert maximization to minimization. So there's one less thing that we have to do. We no longer have to worry about minimization as a special case ever again. We can now consider only maximization problems for the immediate future. Here's a time to talk about some notation. It's good to bring in new notation as often as we possibly can. So every now and then I'm going to want to talk about a sequence of inequalities, and we'll see in a few minutes where this is going, but there are times when, because I have a sequence of linear inequalities, I might want to use vector notation to make it look more compact. So what I will do is define this notation vector less than or equal to. So when I say that the vector x is less than or equal to the vector y, what I am saying is that every element of x is less than or equal to every element of y. So it's an element-wise less than or equal to. There's no weird normalization or length or dot product shenanigans here. I'm just comparing each element by element between the two vectors. So if x is less than or equal to y, every element of x is less than or equal to the corresponding element of y. So I guess we're at a point where we can actually begin defining what a linear program is supposed to look like. So a linear program, whether it's maximization or not, although we can safely assume it always is said to be in standard form if the following conditions apply. Every single constraint involves a less than or equal to sign, and the right-hand side is a constant. Because you might observe, if I didn't require this, it would be pretty easy to say, well, every constraint involves less than or equal to sign because I could just mirror it and make a greater than or equal to sign look like a less than or equal to sign. So it's not just that. I want only less than or equal to, and I want the right-hand side to always be constant. The left-hand side also has to have this form. Now, really what this is saying, if you compare it to the thing above, is that the left-hand side cannot have any constants. So this constraint here, x plus y is less than or equal to 7, this is in standard form. But this isn't. If I have a constant on the left-hand side, it is not in standard form. The expectation is that we take any constants that we have and we merge them in with whatever's on the right-hand side. Now that's pretty easy. All I have to do is move this over. So 7 minus 6, which means this is less than or equal to 1. So it's not in standard form unless all of the constants have been merged into one constant term on the right. There is a less than or equal to sign, and the entire left-hand side is a linear combination of optimization variables, and that's it. So a problem is in standard form if the constraints obey those criteria, and if every single variable is forced, or every single optimization variable, I should say, is forced to be positive. There is no requirement that the coefficients of linear combinations or the constants be positive, but the optimization variables themselves are required to always be subject to these constraints xi is greater than 0. This is pretty strict. I have imposed a lot of conditions, and we can think of lots of optimization problems in practice where, for example, we might want to work with negative numbers, or where there might be greater than or equal to signs or equals signs showing up. When I'm saying an LP is in standard form if these things apply, I guess I have to provide some pathway for what do we do with linear programs that aren't in this form. So the goal of this lecture, the majority of it at least, is to prove that you give me an LP in any form that is a linear program, and I can find some way of turning it into a linear program in standard form. Often the way that we do that is by adding more constraints or more variables. If I have an LP in standard form, I can always write it like this. I can represent it in long form looking like this, or I could view each row as a vector equation involving a vector AI. So here's row I. So this would be A1, A2. I define a vector for the coefficients in each row. I define a vector C of all of my objective function coefficients, and then I could write it with vector notation. I could say I want to maximize the product x dot c plus this constant d, subject to a1 dot x is less than b1, a2 dot x is less than b2, and the every optimization variable x is greater than or equal to 0. So one of the advantages of standard form is now if I'm thinking about, oh, I want to solve this LP with a computer program, how am I going to represent the LP? Well, because it's in standard form, I can represent it with this pretty predictable grid of numbers. And in fact, I could even use linear algebraic notation to represent the LP, which we'll see we do increasingly as the course goes on. So at some point in June or July, we'll actually revisit all of the material from May from a strictly linear algebraic perspective. A lot of the things, the algorithms we're going to be discussing between now and June, it turns out can also be framed in terms of numerical linear algebra. So we can write the LP like this, where we define vectors for our objective coefficients, for the constraint bounds, and a vector x to refer to our optimization variables. Notice that I'm not using the boldface vector notation in this definition because I'm actually defining an n by 1 matrix. When I use the vector as a vector, I can use the vector, the boldface or not. And then I define a matrix A, which consists of all the constant coefficients of the constraints. And then I end up with maximize this plus d, subject to a times x is less than or equal to b. And here's where I am using, in these two lines, I am using that vector inequality that I defined earlier. Now, another notation note, if I treat c and x as n by 1 matrices, then the dot product c times x is equivalent to the result of matrix multiplication c transpose times x. In this course, I am going to use these two notations completely interchangeably. So other than there are lectures that are focused entirely on linear algebra where I'll probably mostly use this notation. And if it's my choice, if I'm not forced to work with matrices, I will generally use this notation. But I am now giving myself a complete license to use dot products and this n by 1 matrix multiplication c transpose x interchangeably, because I define them to be equivalent under the usual assumption that we can view an n element vector as being an n row and 1 column matrix. So if I want to frame it truly in linear algebraic terms, I would probably write it like this. I wouldn't use a dot product because I am using matrix products elsewhere. Often, and when I say often, I actually sort of mean always, so pretty much from now on, we are going to omit any constant that shows up in the objective function. So we're going to assume that the objective function is pretty much entirely a linear combination of the optimization variables. And the reason is, maybe you can prove this to yourself, but if I'm just adding a constant to the end of my objective function, I don't need that to participate in my optimization. If I find the maximum value with the constant ignored, the maximum value with the constant is just that plus the constant. So what I can do is I can say, observing that the minimum of f of x plus d is just equal to the minimum of f of x all plus d. Because of that, it's easier for me to just get this off my plate. Just ignore any constant in the objective function. And so going forward, we are going to define that there is no constant in the objective function when we're working with LPs in standard form. So that brings me to this. I have defined standard form. I think described why I think it is pretty ambitious. There's a lot of restrictions I'm imposing on myself by requiring an LP to be in standard form. So now I've got to put up or shut up. Is it true that I can take any LP you give me, any linear program which is a bunch of linear constraints and a linear objective function, regardless of how they are stated, and I can put it into standard form so that the set of all possible solutions is identical? So if I solve the standard form version, I have solved the original. I have to show that that's actually attainable. Any LP can be put into standard form. Now, this is saying minimization or maximization because it is still going to be significant to us in this course that a minimization LP is distinct from a maximization one. But we know from earlier that if I want to solve an LP, it's sufficient to just solve the maximization versions because I can convert minimization problems to maximization problems. So let's consider this LP, and it's got some behavior that, there's some things happening that are definitely not standard form. And I will call attention to this thing, an equality constraint, something we haven't spent much time thinking about until now, and this greater than or equal to inequality, where it might be more obvious what to do about this. In this case, the LP already obeys the constraint that, or the restriction that every optimization variable be non-negative. So we don't have to worry about how to get around that problem. We'll see in a few minutes what we do in the event that we have optimization variables that are allowed to be negative, how we adjust the linear program to account for that. So for right now, though, let's see if we can work around this greater than or equal to inequality and this equality constraint, how we can turn this into something that is in standard form. So the first thing is the greater than or equal to sign. That turns out to be relatively easy to work around. We could just multiply everything by -1, essentially. We could flip the sign. And there are a lot of ways to justify how that works. I think the easiest way I would say is what you could do is you could move the b over here where it becomes -b, and you could systematically move all of the a terms over to the right-hand side. So you'd get -b is greater than or equal to -a1x1 minus -a2x2, and then you have all of the a's on, you have a constraint arranged so that it's a less than or equal to. So fundamentally what you're really doing is just multiplying everything by -1, but if you want to justify that algebraically, you're just moving every term to the opposite side of the inequality. So we can convert a greater than or equal to a less than or equal to by just multiplying everything by -1 and then flipping the inequality. Okay, so now we've taken care of this. That's now sorted out. Then what do we do about equality constraints? So equality constraints, if we think about it, because of the usual property that we've got, if I know that C is less than or equal to D and C is greater than or equal to D, I'm saying that the two things are equal. So I could employ that strategy in reverse. If I want to say that C equals D, and I'm not allowed to use the equal sign, I could just state two complementary inequalities. I could say, well, C is less than or equal to D, and C is greater than or equal to D. And then I then have two inequalities, and then I apply the same logic I did on the previous slide to force that greater than sign to be a less than sign. So if I have an equality constraint, I can turn it into two less than inequalities by first expanding it into a less than and a greater than, and then taking the greater than side of it and expanding and rewriting it as a less than or equal to sign. So I'm doing the same operation as on the previous slide with half of this doubled constraint. Okay, so I found a way of turning equality constraints into less than or equal to inequalities. And that means this linear program I started with over here on the left, modulo a typo. Sorry about that. We're not supposed to change max to min there. I'm maximizing x plus 2y plus 3z on the left, and I'm still doing that on the right. And I've adapted all of these non-conforming constraints by applying manipulations. So in this case, I have turned this constraint into this one. I've just negated both sides, and I've used a less than or equal to sign. And the equality constraint has been turned into two complementary inequality constraints. And so now I've got an LP in standard form. What do we do here, though? So here I have an LP whose constraints, these two look good. They're already less than or equal to constraints. But I have explicitly written, for the sake of, being dramatic, that x and y are unconstrained. Now, to be clear, if you ever see an LP that doesn't have constraints on any variables, so here, this LP says 2x plus y is less than or equal to 10. Negative x minus 3y is less than or equal to negative 10. It says nothing about x and y. If you see an LP that looks like this, you must assume x and y can be any real numbers. You can't assume they have to be positive. I am not required to tell you that variables are unconstrained. But because I'm being nice, and for the sake of argument, suppose that I'm explicitly saying x and y are any real numbers, they can be negative, you have to let them be negative if necessary. How do I put this in standard form? So one of the requirements of standard form is that all variables be non-negative, that they be positive or zero. So what do I do to this? Well, in the previous example, I was able to adapt these non-conforming constraints by making new constraints. In this case, I had to add two constraints to accommodate one equality constraint. In this example, I've got a problem with variables. I have variables that have more range than they're supposed to. My solution will be to add more variables. So what I can do is I can take, if I have a variable x that can be any real number, and I want to write it in terms of two variables that are, or in terms, well, I gave it away, in terms of variables that are positive, what I could do is I could take two variables and I could take their difference. In fact, I could make up two variables, x plus and x minus. And if I have x, and then I could say x equals that. So my original variable x, which could be any real number, is now a combination of two positive numbers. So x plus is greater than 0, x minus is greater than or equal to 0. If I want to represent the number, let's say x equals negative 5, then I would take x plus equals 0, and x minus equals 5. And you can see both x plus and x minus are non-negative, and x does end up equaling negative 5 as a result. And so I have this transformation that I can employ. If I have any unconstrained variable, I can just replace it by two constrained variables and then define my original variable to be one minus the other. And so I'm actually going to reproduce the example I just wrote. So if x equals 5, then I get x plus equals 0 and x minus equals 5. Now, you may be looking at this and wondering, well, wait, I don't necessarily get that because I could also have x plus equals 2 and x minus equals 7. And you're right. Both of those would be valid. By introducing extra variables, I am making it so that there could be multiple different solutions for a particular value of x. That isn't really a problem. We've seen in previous lectures, it isn't really a big deal, especially in linear programs, if the optimal solution happens in more than one place. Certainly, this might add to the complexity of solving it, but it does mean we can put it in standard form. And so if I do this, I do end up with a situation where I've added a degree of freedom. And therefore, there could be a lot of different ways that I could achieve x equals 5. But I will still get a solution if I solve the LP in standard form where x equals 5. If I take the difference x plus minus x minus, if I take this, I will still get x equals 5. It's just possible that my solver has a lot of different ways that it's going to get me there. It could give me a lot of different values for x plus and x minus. Although, if you happen to be watching this lecture near the midterm, it would be worth considering, given what you hopefully have learned in the meantime, that the LP solver you're likely using, if it's the simplex method, very likely does choose this solution here. It turns out that the simplex method really likes setting variables to 0 if it can. It's less likely that you'd end up with a solution like this. But in any case, I have some avenue that allows me to replace an unconstrained variable by variables that meet the requirements for standard form. And so if I apply this substitution to the LP, I end up with an LP on more variables. which, I mean, obviously, maybe that's going to be a performance problem. But it turns out that the algorithm we're going to develop in the next lecture really, really relies on all variables being non-negative. Because that allows us to use the potential negativity of a variable as a stopping condition, as a way of not moving any further in a particular direction. So having these requirements on each variable really helps the simplex method. So doubling the number of variables in the LP could have impacts on performance, but in exchange, I can then solve the LP with the simplex method. So if I then put if I do the substitution, I get all these things where I replace y with y plus minus y minus. If I then expand out the terms, I get this LP here, which is sort of ugly looking, but does meet the criteria for standard form. All right. So that's actually it as far as standard form is concerned. I have a way of putting any LP into standard form by replacing unconstrained variables with pairs of variables, by replacing constraints that aren't less than or equal to inequalities with less than or equal to inequalities, maybe adding more constraints in the process. I want to go a step further, and we're done talking about standard form. So this LP here is in standard form. That's what it means for an LP to be in standard form. It has to look something like this. I want to go a step further, a little bit closer to being able to solve the LP. What I want to do is I want to get rid of all of the inequalities, except, I guess, these ones. So maybe we can appreciate why standard form might help us if we're writing algorithms to solve LPs. Because by using standard form, we no longer need special cases for things like the greater than or equal to sign or the equal sign. Because we know that if you put the LP in standard form, all I'm ever going to see is a less than or equal to sign, except of course that I'm constraining all my variables to be non-negative. I want to go a step further. I want to write the LP in a form by adding more variables, where there is only one type of inequality, and it is this one. The only actual inequality constraint in the LP ends up being this every variable is non-negative. So what I'm going to do is I'm going to introduce a bunch of extra variables to essentially absorb the extra information embodied by this less than or equal to sign. So let's first do a bit of algebra. So if I have a constraint like this, the typical standard form constraint, I can rewrite it. I know this seems like a step backwards. I can rewrite it as a greater than or equal to 0 by basically moving everything over here to be over here. So it ends up being 0 is less than or equal to b minus this, minus this, minus this. So I get this situation. And I promise I'm going somewhere useful with this. I'm not just walking backwards through the standard form description. Okay, so I can rewrite any constraint in standard form as a greater than or equal to 0 constraint. And then I observe, what is this actually saying? Okay, this is saying that whatever you have on the left-hand side is greater than or equal to 0. Now, it could be like 10 or 50 or 100. But what this is saying is there might be a gap between this thing and 0. But that gap is going to be some positive number. Obviously, if the gap between this thing and 0 were like -10, that would mean this thing is less than or equal to 0. So when I say that this thing is greater than or equal to 0, I mean that there might be some distance between it and 0, but it's some positive number, or maybe it's 0. So I could actually rewrite it like this. I could take this constraint and I could write it as W equals that stuff from the previous slide. And W is guaranteed to be greater than or equal to 0. In other words, this is always greater than or equal to 0, and we'll just define whatever it comes out to be a variable called W. So we're now defining a variable to be the slack between this constraint and the number 0. And we'll call W a slack variable. So W is going to equal 0 if and only if the constraint is being met at equality, if the constraint is operative. And we might remember from the previous lecture that a constraint is met at equality if you are standing on the boundary of the feasible region defined by that constraint. The slack variable W is going to equal 0 if and only if the constraint is met at equality. And W will have a positive value if the constraint is feasible but is not met at equality. So if this is strictly less than the value B, then the value of W will be positive. And under no circumstances, if the constraint is met, will W be negative. I can do this for all of the constraints in the linear program. And you might see I've decided I'm going to start writing the linear program out in a little bit different of a representation. So what I can do is I can define a slack variable for every single constraint in the linear program. And the way that you should think about me doing this is, what I do is I just transfer every variable over to the right-hand side. So there's minus x, and then I've got to move y minus y. Okay, so that means my first slack variable would be w1 is 8 minus x minus y. If w1 is 0 or positive, that means that my original constraint over here is feasible. That means that x and y meet the criteria for the constraint to be feasible. So I do the same thing with w2, w3, w4, w5. And if I do this, what I end up with is a constraint system where the only constraints that exist are on variables themselves. Because I've defined these slack variables to be surrogates for each constraint, the only constraints that exist are that every variable in my system, x, y, z, and all the w's, is greater than or equal to 0. So I've managed to reduce my linear program, which is a bunch of linear algebra with inequalities, to a place where it's a bunch of algebra with only one type of inequality, and that's this greater than or equal to sign, which now applies to every variable. Maybe you can take a moment before we go further to sort of admire the consistency that we get there. We get this nice sort of symmetric sense that every variable in my system will now forever be non-negative, and that's the only constraint I ever have to enforce. And that's sort of evident in the way I've written it out. Notice how I've written this as a system of equalities now. It's strange, we've jumped back and forth in this lecture between going to standard form, which involved eliminating equality signs, and now jumping from standard form into this representation, which brings them back. But now all I have are equal signs, and this implicit greater than or equal to 0. So I earlier mentioned that if you see an LP written in this form that doesn't have constraints on the variables, you are required to assume that the variables are unconstrained. On the other hand, when I use this form over on the right, which we call a dictionary, which I think there's a definition about 3 slides later, when I use a dictionary, whenever I represent it with this dictionary form, every variable, except for the top row, which is the objective function, is assumed to always have this non-negativity constraint. The reason why this is so helpful is that it means I only ever have to think about one type of inequality, and that is every variable is non-negative. And it also turns out that it emphasizes a certain interesting property of linear programs, which is that really, if I write it this way, it looks a lot like I'm just defining every variable in terms of other variables. W1, this constraint, is really just a variable defined in terms of x and y, and so is w2. In a sense, that means that really w1 is sort of, you could rewrite w1 to be defined in terms of w2 and w3. It's just a system of equations. And of course, we're going to come back to that aspect over and over again. So we call the thing on the right a dictionary. And to be clear, if you see a dictionary, whether or not I tell you it's a dictionary, if it's in dictionary form, you must assume that every variable I use is subject to a non-negativity constraint, whether I write it or not. If I write out an LP, and I don't say it's in standard form, so if I say the LP is in standard form, then this should be present, but if I've omitted it, that might be an accident. If I don't tell you an LP is in standard form, unless I explicitly constrain variables, you shouldn't assume that they're going to be non-negative. And also, as you might notice, I don't use the word max or min over here. In this course, if I use a dictionary, I am referring to a maximization problem. Because I have this nice tableau representation where I've got W1, W2, W3, I've got an equation for every constraint, I have to have the objective function in my dictionary somewhere. So I put it up at the top. I always draw a line between the objective function and the rest of the stuff. But I feel like it would be weird to not give it a name. Every other row has a name. So what I will do is I will name the objective function row zeta. And we can see we're only 5 lectures in, and I'm already beginning to have to use Greek. It's not going to get any easier, unfortunately. So I'm going to use this row zeta to refer to my objective function. And we're going to see later that the dictionary form actually reveals a huge amount about the linear program, far more than is obvious from the sort of modest way that it's being written here. And we'll begin to converge on that in the next lecture. But it turns out that this number here, the constant on the objective function, and you might remember a few minutes ago I was talking about how we were going to be deleting constants from the objective function, and yet here I am bringing it back. Because I have a column full of constants that I'm using on the w's, I felt like it's only fair to give the objective function its own constant here. It turns out that that's going to be very significant. But before we talk about that, let's talk about this. Here is a system of equations. I have gone out of my way to not make this look like a linear program. So it's just a system of equations. I'm defining some variables in terms of some others. We might notice that I'm defining a and b in terms of a, b, c, and d. And in particular, both a and b are sort of defined in terms of each other. So the first thing I want to point out is that if I give you this system of equations, I change nothing about the underlying relationships by rearranging terms. A equals 2b minus c. B equals a plus c plus d. What if I rewrite these in terms of c and d? Okay, so let's try this. So c, I know it's down here, but I'm just going to do it by hand. So wait, c equals, let's see, we've got a minus 2b. I don't know if I believe that. I think that might be a typo. So I think that c equals 2b minus a. So it's a good thing I did it by hand. And then I want to rewrite this in terms of d. So to me, that sounds like d equals b minus a minus c. So I'm just going to call this one a typo. And it's a good thing I tried working that out by myself by hand. So the point I was going to make, which I can make either way, is that by rearranging terms, I changed nothing. Nothing about the underlying relationships of variables. This representation does not change anything about the relationship between a, b, c, and d at all. All I've done is found a different way of representing it, period. And the reason I have to bring this thought experiment up is that what I'm about to show you on a dictionary looks a lot like I'm performing some manipulation, some sort of magical manipulation, but I'm not. I'm rearranging terms. If I rearrange terms, I am changing nothing about the relationships between variables. What I might be doing is making it easier for me to understand those relationships, but that's it. So here's another example. I'm actually going to save this one for a live lecture, both because I don't know if I want to trust my slides, but also because I want to have a good excuse to pontificate more about this in a live lecture. So let's take a look at this LP. I've written it in standard form, and I've written it as a dictionary. And of course, the example is mostly going to talk about this dictionary representation. Actually, it's not fully in standard form because I've added a constant here. The reason I've added a constant is for the sake of having this constant not be too lonely. It gets to be a value that isn't equal to 0. Okay, so I have this. And I stare at the dictionary form. And I notice that in the dictionary form, what I'm really saying is actually that the constraints represent a system of equations. I'm really stating W1, W2, X1, and X2 in not too different a way as I might be talking about A and B or these equations in this thought experiment. I'm just stating a bunch of relationships with an equals sign. Is there really any reason that I shouldn't be allowed to rearrange terms? And the answer is, well, no, I should. I can rearrange terms all I want. So let's try this. I know that W1 equals 4 minus 2x1 minus 4x2. I have that from the dictionary form. If I wanted to, I could rewrite that in terms of x1. So I could say, well, okay, if I move x1 over here and I move w1 back, I get 2x1 equals 4 minus w1 minus 4x2. And then if I just want to know what x1 is, there's x1, that equals 4 over 2, which is just, I'll do the whole thing. I divide the whole thing by 2. So x1 equals 4 over 2 is just 2 minus 1 half w1 minus 2x2. So of course, it's a system of equations. I am welcome to solve one equation in terms of some other variable all I want. Okay, so I happen to know that x1 is equal to 2 minus w1 over 2 minus 2x2. Okay, great. What does that really do for me? And I stare at that for a minute, and I think, wait a minute. I'm using x1 over and over again in my dictionary form. What's stopping me from rewriting the dictionary with this plugged in for x1? And the answer is, well, wait, nothing. what I could do is I could observe, I know what x1 by itself equals, and I also know that if x1 is equal to this expansion that I have here, anywhere I see x1, I can sub in this. And so I do. Okay, so in my dictionary, gamma equals, so the objective function is 1 plus x1 plus x2. So I know what x1 is. It's that equation I just came up with a minute ago. So I sub that in, and I get this. Okay, and then W2 is equal to 8 minus 3x1 minus 4x2. So I sub in that expression for x1 that I got a minute ago, and then I get this. Okay, where's this going though? And then what I do is I notice, okay, so I previously had this whole column that used x1. And I took this row and I rewrote it in terms of what x1 actually equals. So I took this row and I rewrote it to be x1 equals 2 minus 1 half w1 minus 2x2. And then I think, you know, I guess back what I had before, w1 got a row to itself. But now I've written that row in terms of x1. And when w1 got a row to itself, w1 didn't appear anywhere else. What if I want x1 to get the same treatment? What I could do is what I've done on the next two slides. I take this definition for x1 and I say this gets to be a row of my dictionary now. And then I plug in the expansion on the right-hand side everywhere else I see x1. And that'll be a way of getting rid of x1 from that column. So I end up with this. And this is all, I know there's quite a bit going on here. The next lecture will talk about this in much more detail. But I want to talk about this idea of manipulating this system of equations, because that's what I have, just a system of equations. I started with this, a row for W1 and a row for W2. I found a way of rewriting the row for W1 to look like, this. It's now been phrased in terms of x1. I then take that definition for x1 and I plug it in to the other two functions where they use x1. And in so doing, I end up with an expression for the other two functions that doesn't use x1 at all. Instead, it now uses w1 and x2. And so I end up with an expression for gamma that uses w1 and x2. And they end up with an expression for W2 that uses W1 and X2. And notice the interesting symmetry here. In my original dictionary, I had these two variables, W1 and W2, that never appeared on the right-hand sides, and these other variables, X1 and X2, that always appeared on the right-hand sides. In my new dictionary, if I may be so bold as to call this thing a dictionary as well, in my new dictionary, I have X1 and W2, two variables that only ever appear on the left-hand sides, and I've got W1 and X2, two variables that only appear on the right-hand sides. The next thing to observe is these two things are the same. So I mentioned earlier in our thought experiment, I demonstrated that if I have a system of equations and I rearrange terms, nothing changes about the system of equations. They're the same. I've just found a different way of looking at them. All I've done here is rearrange terms. I have found two equivalent dictionaries for the same linear program. Now, it's true that in our next lecture, we're going to see a way of interpreting these dictionaries that allows us to draw some pretty startling conclusions. But fundamentally, these two dictionaries describe the exact same set of relationships, the same set of linear relationships between variables. And so nothing really has changed. I have not modified the system. The other thing I might observe, so this is a way of proving this point. Suppose I set a bunch of variables. Over on the dictionary on the left, if I set x1 to be equal to the number 2, and I set x2 to be equal to 0, you can verify this to yourself, I guess, but it turns out that I get W1 equals 0, so 4 minus 2 times 2, fair enough, and I get W2 equals 2, so 8 minus 3 times 2 would be 2. Okay, so I get this assignment of variables if I plug in x1 equals 2, x2 equals 0 on the dictionary on the left. Suppose that I plug in the same variables on the right. So if I have, on the right I'm using... let's see, I've got my independent variables are W1 and X2. So W1 equals 0, so I set this to 0. And I set, X2 is equal to 0. This one should be easy. Okay, and that gives me X1 equals 2 and W2 equals 2, which looks about right to me. So these are the same, really these two dictionaries describe exactly the same thing. I can prove it because if I plug in numbers, I'll get the same numbers both ways. I'm just getting them by doing a different sequence of operations. Notice also that in both cases, I have met all of the criteria of those non-negativity constraints, just sort of incidentally. Now, the procedure that I just did, rearranging the variables in the dictionary, solving one equation for a variable that appears on the right-hand side, and then subbing in that new equation everywhere else it appears, so that the variable I solve for gets its own row in the dictionary, that operation is called pivoting. And you can take a moment to think about other places you have heard the word pivoting applied to a system of linear equations. I'll wait. Well, you can pause it. Otherwise, I would wait, and you could think about that. Although I rearranged the dictionary to expose different relationships, I didn't change anything about the underlying system. And therefore, if I were to, for some reason, use this dictionary to solve my original maximization problem, anything I deduce from this dictionary would be a valid deduction on the original dictionary and the original LP as well. The goal of my original LP was to find the largest possible objective function value. And if I perform some manipulation involving pivoting on my way there, any observation that this dictionary helps me make will still be applicable to the original LP. And speaking of observations, isn't it interesting that after I performed that pivoting operation, this number, that constant attached to the objective function, got larger? And I might think to myself, it's interesting that if my goal is to make the objective function as large as possible, to maximize the objective function, how convenient that by rearranging equations, I was able to get this constant, this positive constant appearing in the objective function to look a bit bigger. So maybe that's something worth thinking about.